Welcome back, algebra students, and today we are going to take our second step into solving linear systems by substitution. I'm glad to hear that so many of you love using substitution rather than graphing to solve your linear systems. Sometimes it's just easier using the algebra. So today we're going to take it a step further and solve linear systems from the real world. So this is day 2, real world systems of equations. So to kick it off, I'm going to show you a table that we can use as an example of a real world system of equations. We're going to use the table to find the number of weeks at which the total cost of weekly produce will be the same, whether you shop at a club store like Costco or Sam's Club, or you shop at a retail store like Vons or Ralph's or Albertsons or Fresh and Easy. So when you're shopping at a club store like Costco, there is typically a club fee involved. In this example, the membership fee, the annual membership fee, is imagined to be $20 a year. And when we look at the retail store, there is no annual membership fee. Anyone can walk in the door and purchase the merchandise. So the deal is, with a club store like Costco, you might have to pay that membership fee. You do that so you can get the deals. So as we look at this example here, the deal is each week the same amount of produce would cost you something different depending on where you buy it. So at Costco, the produce would cost you $15 a week, while at a retail store like Vons, that same produce would cost you $17.50 for the week. So what we want to do is take this information and place it in the form of 2 equations that we can solve to tell us what week the total cost of produce would be the same whether we shopped at Vons or at Costco. Hopefully this information feels familiar because all year we have been creating linear equations from similar types of problems. So when we look at Costco, let's see if we can put that into a linear equation. Do you see a rate? Do you see a rate given in this table? And so when we're looking for rates, we're often looking for a number with 2 different unit forms. So which of these terms here, $20 or $15, comes along with 2 different unit forms? Would it be the annual club fee or the cost per week? Well, ding, 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 there's that word per. So we know that we have 2 different unit forms in this $15. And when we have a rate, where do we place that in our linear equation? You got it. It's our slope. So we will consider 15 to be the slope, and I'm sure by now you have thought about what that $20 might represent in a linear equation. And yep, it's a starting place, and our starting place classically becomes our y-intercept. Okay, so we could say the same thing for the equation we want to write for Vons, right? We could say that we have a rate down here, $17.50 per week, and a starting point. The starting point for Vons is none. And what would none be as a number? You got it, it's $0. So we can simply take the information given and put it in the form of an equation. And let's see what we have. The total cost for Costco would be, if we're going to use our favorite form, y equals mx plus b, let's just take the m and put it in the place of our slope and the b starting point. So for Costco we have 15x plus 20. And for Vaughn's we have y equals 1750x plus 0, or just 1750x. So these two equations represent what's going on at these stores, and now we want to find out when these two equations are equivalent. So we can basically take 15x plus 20, which equals y, and set it equal to 17.50x, which also equals y. Both of these represent y. And so we set them equal to each other, and we'll just solve. And how do we solve this? Why don't we subtract, and which side has the greater coefficient of x? The right side. So let's subtract 15x from both sides. And to finish this, we notice that x is being multiplied by 2.5, so let's divide both sides by 2.5. Okay, so we have x nicely alone, and what can we do about a decimal in a fraction? Why don't we use our method of blowing the fraction up, so we can multiply both top and bottom by 10, and that would give us 25 in the denominator and 200 in the numerator. And how many quarters are in 200 pennies? We know that there are 4 quarters in 100, so there must be 8 25s in 200. So we now have the week in which these two stores would have the same cost, and that is the 8th week. Okay, the second problem represents a mixture problem, which really feels tricky, but is just simply a system of linear equations once again. And so you may need to pause this screencast so that you can take down this problem for your notes. It's a great one to have as an example. A chemist needs 15 liters of 60% alcohol solution. The chemist has a solution that is 50% alcohol. How many liters of the 50% alcohol solution and pure alcohol should the chemist mix together to make 15 liters of 60% alcohol solution? This sounds so painful, but really we'll find it's very doable. So again, we want two equations in this system. First of all, we know that he or she ultimately wants 15 liters of solution. And so we'll begin with saying that there are two types of solution. So let's call the 50% alcohol F, and we don't know how much he needs of that yet, so we'll just call it F, the amount of 50%. Plus, he also has pure alcohol, let's call that P. So when we know how much of each of these he has, we will know that their sum is 15 liters. Okay, so we don't know how much he needs of each, but we know that when we add that together, it will total 15 liters. Secondly, we know that the 50% solution is made of 50% alcohol. And what is 50% as a decimal? 0.5. And when the chemist adds 50% alcohol with the pure alcohol, which is pure alcohol, what percent is that? Oh, 100%. So let's put that in as a decimal. 100% would be just 1. When we place that together, whatever those exact amounts are, will total what we want, which is 60%. And it will be 60% of how much will be in that total mixture? That's right, 15 liters. We actually know how much the total mixture will be. So we have two equations, and we now can use substitution to solve. F and P in our equation A have the same coefficient, so either one of these is we could isolate easily. When I look at equation B, P is kind of all by itself, so it would be really easy to substitute something into that. So for that reason, I'm going to isolate P in equation A. To isolate P, I will subtract F from both sides. We're just going through the steps of substitution. We'll take this expression equal to P, which is 15 minus F, and substitute it for P in equation B. All right, and so now we have an equation with just the variable F, so we know we can solve for F. So let's do it. If I have 0.5 F and negative F, that's a negative 1F, I ultimately have negative 0.5 F plus 15 equals, what is 0.6 times 5? Well, 6 times 10 is 60. 6 times 5 is 30, so that would be 90, but I've got one decimal place. So instead of 90, we have 9. All right, let's go ahead and subtract 15 from both sides. Nine minus 15, negative 6. So at this point, we're ready to divide by negative 0.5. That gives us 1F, and I have a negative being divided by a negative. And once again, I have a decimal in my fraction. We can change both of those terms to positive terms. Negative divided by a negative is a positive. And what is 60 divided by 5? It is 12. All right, so F represents our 50% mixture. So we have 12 liters, it looks like, of 50% mixture. And so we're going to take that and substitute it into the equation for P. P equals 15 minus F, we can see. So we'll just substitute 12 for F, and we know that our pure mixture is 3. So we will need 12 liters of 50%. And 3 liters of 100%. Yay! Woohoo! We did it! All right. And so don't forget to check for reasonableness in your equations. Does it sound reasonable that if I have 15 liters of a mixture that is 60% alcohol, that I might have a lot of 50% alcohol and just a small amount of the pure alcohol? That sounds reasonable in the real world from my experience. So always check for reasonableness at the end of your problem, and that common sense can get you through too. So just as a quick check. And keep in mind, these linear systems solved by substitution can not only be done pretty easily by substituting, but also can be tons of fun. So have fun doing your assignment.